So, yeah, first, how do we fill out the blanks here? No. Emily, what did you guys get in your discussion with our 23 pairs of homologous chromosomes? Yeah, one from your mom, one from your dad. So, for example, this one, I'll say this is mom's, and this is dad, and I think these symbols are used for male and female. I'll use them from time to time, so maybe get used to that. So yeah, you have 23 pairs, and you get one from your mom, one from your dad. Okay, so a set of genes. So say for example, this gene A is eye color. This gene right here is for, we'll say it's hair color. And C, what trait could C be? Give me a human trait. Anything. What's that? Skin tone, yeah, skin color, yeah. And that's interesting. Out of all the human traits, which one do we notice first about other people? What do you think? Out of all the human traits, when we first see somebody, what trait do we pick up on first? Their what? Their face. Yeah, what about their face? Their eyes, maybe? Okay. Anything else? Any other ideas? Hair pattern, hair color. Okay. Hairstyle, wavy, curly, straight. Okay. What about skin color? Do we pick up on that? Yeah. I would argue that might be the first one we kind of subconsciously look at. All right, but we're very cognizant of people around us and, noticing their traits. So these are all different traits. These are different genes located here. You have, say, A eye color gene from the mom, and then you have little a eye color gene from the dad. Big B hair color gene from mom, little b hair color gene from dad. Okay, so these are just, so for hair color, it's the same spot in each chromosome. We'll call these chromosome 1. So chromosome 1, you got 2 sets of those. And by the way, you see how each chromosome is divided? It kind of has 2 halves. Remember, each side are identical. Okay, they're copies of each other. This is a copy of that. They're identical. Remember, normally your chromosomes kind of look like this. That's normal, uncopied. This is the mom chromosome. This is the dad chromosome. When you get ready for mitosis or meiosis, a copy is created. Okay, it's called sister chromatids. In biology, like any subject, AP subject, there's lots of vocabulary, right? In genetics, there's even, I would argue, there's even more vocabulary in there that you kind of have to keep straight, and it gets kind of confusing. So I'm going to try to use these words as much as we can so we can get used to it. So number 2, we have crossing over. Look at what's happening to those non-sister chromatids. So let's get used to that word, non-sister chromatids. So the non-sister, they're non-sister because, are they from the same chromosome? No, they're from the mom chromosome and the dad's chromosome. Which ones are sister chromatids? Which ones are sister? It would be this half and this half, right? Or this half and this half. If it touched each other, that'd be, sister chromatids. But they don't cross over. It's the non-sister ones that cross over. So what happens to those genes, Jacqueline? When you have this crossing over right here, what happens to these letters? Okay, they combine. Give me specifically, how do they combine? Like they go from this configuration, see how it's ABC? Big A, big A, big A, big B, big C, to big A, big B, little c. So what's happened to these genes? They switch, yeah, so the genes can switch between non-sister chromatids. Genes can switch between non-sister, write that again, non-sister chromatids. And when we do that, what do you see happening? Instead of before, everything was big A, all the combinations were big A, big B, big C, or little a, little b, little c. What do we have now? Do we have new combinations? Now we have this new combination of big A, big B, little c, and little a, little b, big C. So we have new combinations. We have new genetic material. So new combinations, more diversity. So nature is always mixing things up. It's always reshuffling, recombining to create differences. Nature doesn't want everybody to be the same, Jasmine. Because if we're all the same, we don't survive as well. So by shuffling the genes, it makes us more resistant, it makes us more hardy, allows the species to keep going in the face of change in the environment. If everybody's the same, everybody's susceptible to the same disease, we can get wiped out. So by having that diversity, it makes any species stronger and allows it to survive over time on Earth in a changing environment. Okay. So make a note. You're going to work on the biozone. You'll have some time at the end of the period to do that. There's a demonstration in the biozone that we're going to do an activity. We'll do that activity class. It's modeling meiosis. So just read it, but there's nothing to do on that page. Just keep on going, filling out the next part. So I want to go over some basic concepts in genetics using some history. So has anybody ever heard of the Romanov royal family before? Does that ring a bell? You know anything about, what do you know about the Romanovs, Denise? Royal family in Russia, that's right. Do you know what happened to them? They were killed. They were killed. You remember roughly around what year they were killed, Denise? Okay. So you guys heard of World War I, right? So they were killed shortly after. Oh, you put that away and look at the Romanov packet. They were killed shortly after World War II ended, when Russia was undergoing a revolution.